Philippines Physics Association in UP Diliman. I welcome you all to the 17th Physics Meetup session with the topic Formation of Giant Planet Satellites. So it's the 17th session and you're still with us. Thank you guys. So the Physics Meetup is a collaborative space devoted to building connections and fostering encounters between Filipino physics learners and international scientists like our speaker today. The Physics Meetup is an online outreach seminar in partnership with various organizations in the Philippines and in collaboration with the Physics Without Frontiers of the ICTP, the Abdusalam International Center for Theoretical Physics in Trieste, Italy. Our sessions introduce us to leading experts, allowing us to see glimpses of the scientists' lives and work, and provide interaction and connection opportunities. So, really, the goal is to hope that we will be able to break the stereotypes surrounding scientists and allow us to see their humanness. So, scientists aren't your typical geeky Einstein look. If you've seen the image of our speaker with his blazing red hair, and if you have not yet known, he's also a lead singer in a band. So, scientists are humans.
But
Like every session,
our band is totally geeky. Our band is just is full of
well,
nerds.
yeah, I think they're also professors. I've seen them, and I like the music though. But still, we're human. Like every session that we have at the physics meetup, today is exceptional, for we have been privileged to learn from an inspiring human being who is live right now from the California Institute of Technology, USA. So he's like that character from The Big Bang Theory. If you know him, I forgot his name.
I'll do my best to to play the part.
Okay, thank you, Prof. K. Now, before we introduce the speaker, we would want to give you a glimpse of the event today. We will have actually four things: an open forum right after the speaker's talk, where you can have the opportunity to ask the speaker on the microphone or Zoom chat or the comment section of our Facebook live stream. But as per Prof. K's request, you could actually ask the questions while he's doing the talk so that he'll know if we're still understanding a word he's saying because this is physics and we know that it's not always easy to grasp. Now, second thing, we'd like to have the response from the participants. So we would like you to share your insights right after Prof. K's talk. And then we'll have a closing message. And right after the session, we'll have a networking. So an opportunity to connect with our fellow physics learners and our speaker for today. So we encourage you to take note to your takeaways or lessons learned from the speaker to share them with our speaker and the group at the end of the forum. So without further ado, let's welcome on the virtual stage Professor Lotis Racines to introduce our speaker without further delay. Thank you. So, Professor Lotis?
Hey, yes, yes. uh, Sorry for the delay. Good morning, everyone. I have the pleasure of introducing our speaker briefly for today. Forbes named our speaker the next physics rock star in its 2015 list of 30 under 30 young scientists who are changing the world. Popular Science magazine also dubbed him as the man whose models reveal the possible ninth planet in our solar system in the list of brilliant 10 people in the planet in 2016. He received his bachelor's degree in physics from the University of California, Santa Cruz in 2008 before pursuing graduate studies at the California Institute of Technology. To date, Batygin has authored over 80 scientific publications, and his research has been featured on the front cover of Scientific American. Before joining the California Institute of Technology as a faculty in 2014, Batygin was a postdoctoral scholar at Observatoire de la Côte d'Azur in Nice, France, and Harvard University. When not doing science, he enjoys playing in his rock band, The Seventh Season. Let's welcome on the virtual stage Professor Konstantin Batygin, or Professor K. Hi, Professor K.
Hey, thanks so much for that. Thanks so much for that introduction. And, indeed, it's true. They put me on this list in Forbes magazine, but
Yeah.
unfortunately, the wrong list. I was hoping, to end up on like, the rich list, but instead they put me on this other one, which is, you know, still pretty good. Okay, so listen, it's a real pleasure for me to be spending my Friday evening, you guys, a Saturday morning with you. I think it's really important, and especially at times like these when we're not allowed to travel and see each other in person, to keep engaged and to find ways of connecting through Zoom. So I really appreciate the opportunity to meet all of you guys, and hope that we can have a lively and engaging discussion. And so in the topic that I want to spend some time talking about today is a problem that I've become quite interested in over the last couple of years, and it has to do with the formation of giant planet satellites. So let me quickly share my screen here, and I'll sort of begin discussing what I'm talking about. So I should preface this by saying that I'm not particularly, as a student, I was not particularly good at doing the complicated problems. Just I remember in quantum field theory, just like got all the answers wrong. Just because all the integrals were kind of complicated. But what I was relatively good at was asking the stupid questions. I'd ask my professors dumb things like, where does the Schrodinger equation come from, or something like that. And what I found is that if you ask the stupid questions enough times, eventually you'll stumble upon one that's really interesting. And I think the giant planet satellites constitute one such stupid question on the surface, but one that we don't have an answer to. And so let me just backtrack a little bit. The satellites of Jupiter, okay, all right, Io, Europa, Ganymede, Callisto, were literally the first thing that was discovered in astronomy, right? I mean, when Galileo adopted the telescope as a scientific instrument, he looked up at the moon and jotted down what he saw, but everybody knew the moon was already there, right? So it's not really a discovery. The first real discovery that was made was the existence of these satellites. And over the years, of course, we've known about these satellites for centuries, but over the years, we've learned a lot more detail about them. And in the next decade or so, our detailed understanding of what the satellites of the giant planets in the solar system really look like will get deeper and better and more detailed. And this is in large part due to the next set of missions that will be going and exploring the outer solar system. There are three in particular that come to mind. The first is a NASA mission called Europa Clipper, right? Europa Clipper will go and, as the name suggests, it will clip Europa, the second satellite of Jupiter. There's a European Space Agency mission, which is the center picture here, called JUICE. And JUICE is going to the biggest satellite of Jupiter, Ganymede. So Ganymede is interesting in its own right. It's actually a huge satellite, sufficiently large to convect in its interior and maintain its own magnetic field. Really interesting. And then there's another NASA mission called Dragonfly, which is basically a drone of the type that you can like order online, but a little bit better. That is going to Titan, and Titan is the largest satellite, the large satellite of Saturn. So I think all of these missions are leaving Earth this decade. So kind of over the next 20 years, we will know a lot more detail about, I don't know, about the geology of Europa, for example, and the geology and geophysics of Ganymede, the atmospheric processes that occur on Titan. But I am interested in a much more basic question, which is not to, what do these satellites look like in detail? It's why are they there? Okay, like why are there satellites around giant planets, right? So I'm of course not the first person to, oops, I believe my slides here froze. Yeah, okay, I'm not the first person here to ask, the question ever of why do satellites exist around giant planets. But when I got interested in this problem a couple of years ago, what I realized is that the models for the formation of giant planets are not particularly advanced or modern. I apologize. My dog is about to start barking because there's another dog. If you guys hear a dog barking, it's my crazy dog. Bagheera, go inside. Go inside. Anyway, so if you look at kind of what exists in the literature, there are basically two classes of theories, and the first theory is something called the minimum mass model, which is the idea that you can reconstruct a primordial disk of gas and dust that encircled Jupiter 4.5 billion years ago when the solar system was just forming, by taking the satellites, grinding them down into icy dust, and then multiplying that mass by a factor of 100, because the gas to dust ratio in the universe generically tends to be on the order of 10 to the 2. So that model actually comes to us from the 1980s. Was first proposed by Jonathan Lunine and Dave Stevenson, and it's undeniably wrong. Okay, so there are this model's been around for 4 decades, and kind of there are by now publications that twist every parameter of this model possible and conclude that there is no way to reconstruct it's impossible to actually form the satellites that we see in this model, because the disk that would form it would be so hot that you would never get icy satellites. Okay, and that it's as sophisticated as that. The satellites are made out of ice, and this minimum mass disk around Jupiter would be too hot for ice to condense. So the competing model to this is a different variant called the gas-starved model, which was proposed not 40 years ago, but 20 years ago, around 2002. I don't know, Nickelback was still very popular, right? Still on the radio. I don't know if that's a connecting fact, but anyway, the gas-starved model basically suggests that you have a primordial disk of gas around Jupiter, and this gas disk captures rocks, basically primitive asteroids from the parent nebula, the proto-solar nebula, and from them you make the satellites. And in fact, in this model, you must assume a very efficient satellite formation process, and you kind of have to invoke this huge influx of primitive asteroids from the protosolar, basically from the remainder of the solar system into the orbit of Jupiter to make it work. Now, the reason I'm not going to spend too much time talking about both of these models any further is because in 2021, it's clear that basically both of them are wrong on the detailed level. And the reason it's clear is because for the first time a couple of years ago, we saw what it looks like when giant planets are forming. Okay, so with the advent of the ALMA observatory combined with observations from the Sphere telescope, the first circumplanetary disk was detected in, sort of caught in the act of formation. So these are pictures of the same planetary system called PDS 70. Okay, they're in 3 different bands. And what you see here, of course, at the center is the host star. Okay, that's the star. Around the star is a disk of gas and dust, right? So this is a young planetary system like the solar system, which is only a couple million years old. So it's still, the gas has not yet photoevaporated, it's still there. And what we see, those 2 blobs in the center, are analogs of Jupiter and Saturn, which are undergoing formation right now. And one of them, particularly PDS 70C, I think that one with the bigger blob around it, you can see not only the emissions from the planet itself, but you see emission from clearly a resolved disk of gas and dust around it, which is where presumably satellite formation is going on. So this is, and this is very new. This is like 2019 or maybe even 2020 when the paper was published. So with the ability to interrogate what's happening in these systems as they form, what we've learned is that the way these disks around giant planets form is basically through a process that's akin a little bit to rain. Let's take a step back and notice first that the giant planets themselves, right, these two blobs, are not sitting in the disk itself. They have, through their process of formation, carved out a giant gap. And so you see, right, that there's material missing in the giant planet orbit. That's because they've eaten it up. Also, gravitational torques, basically, once the planet is sufficiently large, prevent gas from coming onto the orbit. Now, if you look at that that disk of material from top down, what it looks like is a disk that's almost in Keplerian rotation, but not quite. Okay, so the material that encircles the giant planet orbits slower than the usual circular velocity that we derive in like the first physics class of the first year of college, right? So it's going slower. Why is it going slower? It's going slower because it's made up of gas, and part of the gravitational force of the planet is being canceled out by a pressure gradient. So the material is orbiting in a sub-Keplerian manner. This will become important later. The other thing that we can do is we can ask the question by doing simulations, by doing hydrodynamic simulations, of what about the vertical structure of this disk? How, right? What would it look like if we went into the plane of the system and looked at it from the sides? What we find actually is that this disk is vertically fed, okay? So you can imagine the planet being here, having carved out a gap. So there's like a wall of gas here. And rather than gas coming in the plane, right, it's instead spilling over vertically, and due to conservation of angular momentum, because it's coming from a shearing frame, as it falls to smaller radius, it spins up and creates a disk. That's what's going on. I know that this has been mentioned already, but please do feel free to interrupt me and ask me a question if something doesn't make sense. I am I'm pretty informal as a person, so you're not gonna scare me or offend me or anything like that. So yes, I believe there's a question. But I can't hear anything. David, do you see anything in the chat box?
Okay. Hi. Hello.
Yes. Can you hear me?
Yeah.
Am I still on?
Here.
Okay.
I'm just curious about this detection of complementary disk in the PDS-70 system. Like you show 3 figures, and the parameter that I don't know is the robust parameter. So.
The robust parameter. I'll be honest. I also don't know what that is. It's some contrast thing, but it has to. So the 3 figures, and let me actually go back here for a second. The 3 figures come from actually 3 different observations, and the important thing, if you look at the bottom, right, like the bottom left of the figure, there's like a little circle that's carved out. I believe that's supposed to be representative of the precision of the observation. So you should detect the features you should kind of believe only the features that appear on a scale larger than that blob. And I think the robust parameter is somehow related to that, but I'm really not sure. These are not my observations. I just took these from, from the literature. But great question. Thanks for asking. Okay, so with this picture in hand, okay, and this is a picture that comes to us both from observations as well as the numerical simulations of hydrodynamic simulations of what happens around a giant planet. You might say, as many people in the field do, that hydrodynamic simulations are not particularly reliable for these types of problems because these are high Reynolds number flows and maybe the simulations are overly dissipative and yada, yada, yada. But the truth is that you don't actually have to believe the simulation because this meridional flow has been detected directly also in these observations. Now, where am I going with this? Where I'm going with this is that these days, okay, the picture of what giant planet formation looks like can be summarized in this drawing. And I will confess I did not draw this. My friend James drew this beautiful picture, but it kind of summarizes the main features of what happens when a giant planet is forming. You have the planet itself, which sustains a strong magnetic field. This magnetic field creates basically a magnetospheric bubble, which isolates a little bit of the disk. And the disk itself is fed vertically, okay? And then rather than being an accretion disk, as is typical in astrophysics, right? For example, black hole disks are accretion disks, etc. Disks around planets are decretion disks. The material is coming in from the top and then viscously spreading and then being fed back into the parent nebula. Okay, so the whole picture develops this meridional flow, the slow meridional flow. If you believe this, okay, then satellite formation is in deep trouble. Okay, and the reason satellite formation is suddenly in deep trouble is because if you're grabbing gas from the top of the parent disk, then that gas is necessarily very low metallicity. Why is that happening? It's because it's no different than if I go out to, I don't know, the desert of California or Arizona or something and, kick up a bunch of dust, it's going to come back down and settle. The same process occurs in protoplanetary disks where all dust, all icy and rocky material settles to the midplane, leaving the top of the disk depleted in dust. So if dust is coming in from the top, that means, okay, what's coming in to orbit around Jupiter and Saturn is almost pure hydrogen and helium, okay, very little actual metallicity. And in astronomy talk, anything heavier than hydrogen and helium is a metal. Okay, so ice is also considered a metal. Now, with this in hand, okay, I think we have three problems that we need to solve. Okay, the first of them is, if you believe this picture, how do you ever accumulate enough material around Jupiter or around Saturn to make the satellites? Right? It's a stupidly simple question, but it's one that we have to address with this new picture of a vertically fed circumplanetary disk. Number two, okay, is even if you do somehow accumulate dust and you accumulate enough ice material, how do you then create the building blocks of the satellites? And finally, number three is, what is the process through which these building blocks, the satellite tessimals, actually grow into the satellites, right? Can we have a predictive model that that basically is able to reconstruct the architecture of the giant planet satellite system from scratch? Okay. So to answer these three questions, my partner in crime on this work, Alessandro Morbidelli, with whom I have a decade-long collaboration. He's in France. we set out to basically develop a model entirely from scratch. And what we did first is we said, okay, let's create, just given that the level of sophistication that we're working with does not need to be particularly high, given that we're building it from scratch. So an approximate model will do. What we decided is we just made an analytic model for a decretion disk. And our decretion disk, its evolution equations come from conservation laws, conservation of mass and conservation of angular momentum. Actually, by solving the equations, these conservation laws for a viscous fluid in orbit around a planet, you can actually derive a model for both the surface density profile of the disk as well as its entropy profile. So I don't want to spend too much time on the solution, because the solution is actually, I mean, you can just solve it. It's not a particularly difficult set of equations, but what it gives you is a nebula with a power law like profile, pretty similar to what circumstellar, usual protoplanetary disks look like, except for scaled down around the planet. And the important thing is, the nebula, our model nebula, gets sufficiently cold for ice to condense, but only beyond a particular radius. And that radius is about 1/10 of a Hill sphere. To remind you, a Hill sphere is like a boundary, like a gravitational boundary between where the gravity of the planet dominates and gravity of the star dominates. So the satellites themselves live at only a few percent of the Hill sphere. Their current orbital radii are something like 1% of a Hill sphere. Okay, in this model, this means that we have to form them further out by a factor of 10, and then they have to migrate. That's immediately a requirement of the model. Now, with a model in place for the behavior of the gas, okay, we can then ask the question, what happens to dust grains as we put them into this disk? So remember, the disk itself, okay, and this is super important, the disk itself is subkeplerian, okay? It's orbiting at something like 99% of the Keplerian velocity because of pressure support. At the same time, the disk is slowly decreasing. So it has a background radial velocity, okay, because it's being fed close to the planet and slowly moving out. Now, what happens to a dust grain? Yes, I think there's a question from Austin.
Yes, there. Can you kindly unmute Sir Austin?
Yeah, hello.
Yes, hi.
Hi. What does subkeplerian mean?
Okay, great question. So here, you can, if I go, into orbit of the Earth, right, and my orbit is circular, I can say that G times the mass of the Earth times the mass of me divided by the radius squared is equal to, mv squared over r. And I can solve for the velocity of a circular velocity of a stable orbit, right? It's square root of gm Earth over r. Now, that's the velocity I would have to orbit at in order to not fall, okay? Now, you'll notice, of course, that the Earth's atmosphere doesn't fall on the Earth, even though it's not orbiting at all. And that's because the Earth's atmosphere is in hydrostatic equilibrium. It's entirely maintained by the pressure, by the derivative of pressure, radially, okay? These disks are mostly in orbit, but they feel a little bit of that hydrostatic equilibrium, okay? So because they're made up of gas, they don't have to orbit as fast as a solid particle in order to have a stable circular orbit. Does that make sense?
Yes, it does.
Okay.
Thank you.
All right. Yeah, that's a really great question. It's a really important point because as it turns out, the subkeplerian nature of these disks is both the problem and the solution to how you accumulate enough mass. Here is why. Suppose you are a dust grain, okay, or a baseball or whatever, and you go into a subcaplarian disk. Now, a baseball or a dust grain does not have pressure support, right? It's just a particle. So in order to stay, to be in a stable, circular orbit, it has to orbit at the Keplerian velocity. The background gas does not, okay? So as a result, what a particle will feel is headwind, okay? In such a disk, any solid material will be blasted by a subcaplarian flow. Because the particle wants to go Keplerian, the gas is going subcaplarian. That difference, which amounts to hundreds of meters per second of differential velocity, is going to steal energy from the particle. Now, this is not what follows is not profound. If I throw a baseball on Earth versus throw a baseball in vacuum, of course the baseball it's going through the atmosphere is going to not go as far. So what happens is in these naively speaking, that headwind that's coming from the subcaplarian flow will cause all solid material to decay onto the planet. Okay, this is a huge problem. So how do we get around this? Well, the way we get around this is to notice that there's also a radial outflow coming from the planet, right? Because the disk is decreting back into the parent nebula. And that's described by these two equations. These are just the azimuthal and radial equations of motion for a solid particle in orbit around a planet subject to interactions with the gas, where the things with the dot, the variables with the dot, are the ones that correspond to the particle. The undotted variables are the gas variables. Now, these equations are very well known. Okay, they're cumulatively often called the Nakagawa drift, and what they tell you is what I just said. Right, in a usual disk, particles will fall towards the star or towards the planet, or whatever object they're orbiting, because the particles want to go Keplerian, the dust doesn't. The dust therefore exerts a headwind. In this particular situation, however, we were able to find that these equations admit a new equilibrium that doesn't exist for accretion disks, okay? In fact, this new equilibrium translates to something quite simple. It basically means if you find a particle of the right size, okay, then a particle of the right size will get caught in the disk because it'll exactly cancel the energy loss from headwind from the energy gain from the updraft, which is coming from the radial outflow of the disk. So the way that I imagine this is like if you're on an airplane, okay, and the airplane turns off the engines, right? Of course, the airplane, due to headwind, is going to lose altitude, except for if somebody is running underneath the airplane with a giant fan, right, and causing an updraft. You could, in principle, fly forever without, without any engines. That's what's happening to particles of a particular size in these disks. If you ask what that size is, it's a fraction of a millimeter. Okay, so you can think of it as snow grain, little snowflakes that form in these disks that come in from the top. Even though the gas is depleted, they are the material that can get caught in this disk and never leave. Okay, so this is a really interesting, in my opinion, solution to how to build up the metallicity, the content, the solid content of the disk, because this way the disk basically acts like a vacuum cleaner. It sucks in dust poor gas, right, from the parent nebula, but what it delivers back out to the nebula is just hydrogen and helium. It retains a large fraction of the dust in the disk. I am, of course, oversimplifying the picture when I'm describing it this way. In reality, there's a parallel process of grain growth and grain sublimation, which helps this process along. And if you're interested in the details, I'm happy to describe it. It's not actually that important, but I do want to point out, I guess, that it's not it's not as simple, and of course there are other processes at hand, but the basic idea is that there exists a special equilibrium to the dust gas coupled hydrodynamical equations that only manifests in decretion disks, and that's how you build up enough material. Okay, of course the satellites are not dust, right? If you go and like Io, Europa, Ganymede are not just sand, they are actual satellites, they're actual little moons. So how do you then go from having enough dust to the first icy asteroids? The idea
Prof.
here.
K, there's a
Yes.
question from Mariel Donasco.
Uh-huh.
So, because of the size of these super small grains, the disk isn't too hot now?
So yeah, the disk temperature is mostly controlled by, the disk temperature is predominantly controlled by the disk turbulence. Okay, and so you can actually demonstrate that no matter what you assume, as long as you accumulate this dust at a sufficiently large orbital radius around the planet, it's going to be cold enough. Okay, so the innermost regions of the disk indeed are too hot for the to form the satellites, but at sufficiently large orbital radii, it is cold enough. Okay? So, and this, what I just showed here, I can replay the video. This is, oops, now I need to figure out how to go back. This is basically a simulation of this very process. This is a top-down view of the circum-Jupiter disk, and as material comes in over about 100,000 years, you start to accumulate a huge amount of icy dust. So, with forming a solid subdisk is not enough, as I said. So how do you then convince this disk to form planets? Well, here we have to ask ourselves what this dust actually does. And what we argue in our paper from last year is that if you wait long enough and the dust basically becomes sufficient, the dust content becomes sufficiently large, the dust must settle to a very thin layer. Okay, the reason this must happen is just, we can think about it energetically. Okay, in the desert on the Earth, right? Suppose you have a turbulent day, okay, and or a cyclone or some kind of an atmospheric process which kicks up the dust. Okay? In order to maintain, right, dust in the air, you need to have continuous. You pay an energetic cost. Okay, and certainly the atmosphere of the Earth, no matter how turbulent, will never lift a mountain. So if you just keep on increasing the dust content, you will gradually cause the material to go to collapse close to a smaller and smaller subdisk that is getting progressively thinner. And if you solve the equations, what you will find is that decrease goes down as the square root of the metal content. Okay, so it's square root of the metallicity, square root of the mass ratio, if you will, of everything heavier than hydrogen and helium to that of hydrogen and helium. And then you can ask the question, okay, so suppose I have some disk around Jupiter and Saturn, and then inside of it is some dust, and as it accumulates, it settles to a thinner and thinner plane. Can that go on indefinitely? Can I have an infinitely thin disk of dust? That doesn't seem right. And indeed, if your intuition tells you that you cannot have an infinitely thin disk, you are correct. This is a well-known thing, and it's actually something called the Goldreich-Ward instability, which was discovered in 1973 and has been well kind of well covered in the literature. Basically what it tells you, the basic idea is that if you make a gravitational disk thin enough, a self-gravitating disk thin enough, it will collapse under its own weight. Okay, that's as simple as that. Gravitational systems generically do not owe anybody anything, right? They do not owe equilibrium solutions to anything. And this is in part, by the way, why galaxies have spiral arms, right? Galactic spiral arms are like gravitational instabilities that have been sheared out. That's the tomb ray kind of like that's the tomb ray picture. Of course, in reality, it's more complicated than that. But in a process that's quite similar to the formation of spiral arms in galactic disks or really any disks, this dusty subdisk can fragment into icy asteroids. And what we show in our paper is that the moment you cross the threshold of having about 10% by mass, the ice over gas, large scale gravitational collapse starts to happen in the outer part of the Circumjovian Nebula. And again, here's an animation of that. So we had this dusty disk, and then the dusty disk basically collapses into planetesimals. Satellitetesimals, these satellite building blocks. What you can demonstrate just from analytic calculations is that the satellite disk is actually quite similar to what primitive asteroids look like. So these things are about 10 kilometers across, maybe 100 kilometers, so sort of size of Los Angeles, if you will. Now, the final step in constructing this story is to ask how do these building blocks then actually form the satellites? I noticed that I'm running quite a bit over time, so I'm going to go ahead and skip this part of the calculation and just show you the numerical experiment, which is more fun to look at. Okay, so here's the set of simulations we did. Let me say, okay, we've got the disk of icy satellites. It's all embedded in the icy satellitetesimals. It's embedded within the disk of gas. Okay, so these satellites interact with the gas both through regular hydrodynamic drag as well as through launching waves, okay, once they get massive enough. So and the launching of waves causes migration, as we will see. And of course, the satellites can grow by mutual collisions. So again, this system, okay, this numerical experiment doesn't know anything about the Jovian satellites, okay? It just starts out as a disk of about, 10 to the minus 4 of a Jupiter mass in asteroids, in icy asteroids, and about 10 to the minus 3 in Jupiter mass in hydrogen helium dust. And then you just let it unfold and see what happens. So here, we'll see on the right-hand side, the bars are the mass of the real satellites, Io, Europa, Ganymede, and Callisto. And very quickly, within just a couple thousand years, the first satellite forms to, a magically close value of Io's real mass. And then by starting to launch waves in this disk, they come out of this region where the icy asteroids are and stop their growth. Through this process, you actually keep basically making the same satellite over and over again. And simultaneously, the formation of every satellite messes up the system just enough where the formation of the next one takes progressively longer. Now, if you just allow this system to migrate inwards, what you find is that the satellites naturally lock into something called the Laplace Resonance, where for 4 revolutions of Io around Jupiter, Europa completes 2 and Ganymede completes 1. That's actually what the satellites are doing. That's a consequence of gas-driven convergent migration. Now, I'm not going to spend any time on that, and just say that this process stops at the end of the day when the gas gets photoevaporated by the sun, and as it turns out, after you photoevaporate the gas, there's still one more object that forms in our simulation. And it takes a ton of time. It actually takes millions of years for the final satellite to form. But, you know, again, it ends up being almost perfectly 100% of the mass of Callisto and roughly the right orbital radius. So again, the story that I've told you is not a complete theory. Okay, it is. We've only began working on it. We only have published one paper about this story, but because we're constructing everything from scratch, right? So this is I would say a skeleton of a theory. There's still a ton of work that remains to be done, but given that our numerical experiments have nicely reproduce both the masses and the architecture of the system, I think we're kind of on the right track. So I'm excited to continue this work and just kind of go back, go back to France once COVID is done and keep going. Anyway, I think I'll stop here. I apologize for being over time. I get too excited talking about satellites and go on and on, but I'm happy to stop here and take any questions.
Okay, that was a very, very informative talk that we've had. So yeah, upon listening, I realized there's a lot of things we need to learn in life. Okay, so that's
That's
very
definitely true.
intensive. So thank you once again, Prof. K. I'm sure many of us are quite excited to ask questions. So let me introduce to you our moderator for today. He has a science diplomacy portfolio as the principal assistant to the Office of the United Nations and international organizations, Environment, Climate Change, and International Science Cooperation Division, Department of Foreign Affairs. Let's welcome Mr. Christopher Castillo.
Hey, hello. Good morning. Can you see now on the screen? Can you see me now?
Why don't let me do the stop share.
Okay. So we'll be now on our fireside chat, Prof. K. So if you're Prof. K, I'm Christopher K with a K as well. Kit. Yeah. Okay. Anyway, I do have here listed some questions earlier that perhaps some are shy. As you have noticed, we got diverse participants from the northern part of the Philippines down south. So for our viewers there, you can put in the chat first your location, so at least perhaps Prof. K can see how far wide his reach in the Philippines. I think your provinces will help first. So for us to be more active in our fireside chat. Okay, and as I was saying, they're asking here people from the academe. I mean, this is more of the academe perspective question. Were strong supporters of the long-standing accretionary disk model of planetary formation view you proposed model as considerably contradictory. How do you handle or challenge them? If you encounter contradictions to your model, how do you handle them? Like, that's the recent one that you posted, Napier and et al.
Yeah. Look, I mean, it's the simple answer is, science is not at any point ever supposed to be a final answer to anything. Okay, it's only a successive set of approximations to the truth, and I think that it's important to be skeptical, to push boundaries, and when when somebody proposes something, I think it's really important to try to poke at it. Now, the Napier paper doesn't address anything what I talked about today. It's Planet 9, the work that I've also been really engaged in over the last 5 years. I think that here's what I will say about Planet 9. Okay, there are, if you go on a website like twitter.com or or facebook.com, and you track what happens to Planet 9 over time. Okay, Planet 9 is either, oh my God, it's so real, it's about to be discovered tomorrow, or Planet 9 is dead, it doesn't exist, no. Okay, this is because this is Not true for all problems, but for Planet 9, the news cycle amplifies things by an order of magnitude one way or another. When people ask me, is Planet 9 alive or dead? I like to answer that Planet 9, until we see it, until we actually detect it, it's sort of in the Schrodinger's cat state of simultaneously being alive and dead. Why? Because it's really a theoretical construct. I think the theory, is pretty well grounded in the existing data, and the calculations are right. I mean, it's just not just like, I'm not making this up. There have been other groups that have reproduced all of this stuff. But until we actually detect it, we cannot claim that it's been confirmed or anything like that. What the Napier paper does is it pulls on the question of, okay, Planet 9, the reason to invoke it. There are actually 5, okay, but one of the reasons to invoke it is the clustering of the distant Kuiper belt, okay? And I could show slides on it, but I could also just explain it with my hands. Like, if you go to the far enough away in the solar system, you'll find the orbits are all kind of pointing in the same direction. Nobody is arguing that that's what they're doing. The question is, are they really doing that, or do we only see them doing that due to the fact that telescopes have only looked into one direction on the sky and only detected orbits there? Now, there are 2 ways to, basically what the Napier paper does is they say that if they look at a subsample, a subset of those objects, they can't tell. Okay, so they cannot distinguish one from the other. Or they cannot distinguish if the distribution is clustered, they cannot distinguish if the distribution is unclustered. Okay, this is maybe not too surprising for you, given that the sample that they look at is like 10 or so data points. So this is pretty much typical of all statistics when you have low numbers. What we do to circumvent the low number statistics problem is we take a different approach to doing it. Rather than doing the survey simulation method, we do what's called observability mapping, where you say, okay, there are only so many objects that we care about. But if you look at the total number of Kuiper belt objects on the sky that have ever been detected, there's about 3,000. And you can, and there's information there. So by virtue of the comparison sample being big, you can actually do the statistics a different way. And then you arrive at a different number. You arrive at the probability that they are clusters is 99.8%, which is pretty good. So let me be clear. All this Planet 9 business, I think, remains high confidence and interesting, but also if the data are not clustered, if it's true that the data are not clustered, then everything I did is just wrong. And it's a little bit like, it's a bummer, but it's not the end of the world. Okay, like I think that it's really going to be, I would so much rather propose something interesting and for it to turn out to be wrong than to not propose anything at all.
It's very extensive discussion already, and I'm seeing the dichotomy now of the side of the pro-Planet K and then the non-existent Planet 9. I'm trying to call it Planet K already because of you and Mike Brown. Sorry for that sound from my neighbor. But anyway, another here. You mentioned of the observation, right? Observation and trying to do the simulation thing. So what if there's a question here of what if we come up with a simulation where we also using the challenge with computers or virtual reality thing, where we for example we labeled all the elements in the Kuiper belt, and so at least we can pinpoint easily. Do we have that technology now that we can, in a way, virtual reality thing?
So yes, there are actually there are really cool like visualizations that you can do. I remember I visited the Adler Planetarium, which is in Chicago, a few years ago, and they have a whole lab dedicated to, you walk in with VR glasses, and you can kind of basically swim through the universe. You can use your hands. It uses the Xbox, like the Xbox camera, right? Because the Xbox for a while had this like camera so that you could slash zombies and stuff in real life. So it uses just those cameras, so you can, you know, come up to, you know, go into the center of the galaxy, kind of expand it, play around with the disk, you know, look at the stars, rotate everything. It's really cool. We don't do that in our research. I mean, maybe we should start. I think it would make our you know, it'd be kind of cool, you know, come into work, put on some VR glasses, swim through the solar system. But, you know, jokes aside, we don't actually use that because so much of the work that we actually do boils down to just heavy calculation. And, you know, as cool as it is, you don't need to be like, I don't need to have VR glasses really to do what I do. I can, I have, you know, VR glasses in my imagination, and the rest is done with code and a piece of paper. So well, that said, the other question of, can we use the detections of where things are on, you know, where things are on the sky, particularly in the distant Kuiper belt, to inform the statistics of, you know, the question of, is the distant Kuiper belt clustered or not? The answer is absolutely yes. Okay, and that's not a trivial calculation to do. Okay, but you know, it's one that my partner in crime on the Planet 9 work, Mike Brown, and I have done. And that's the number that I quote from when I say that there's a 0.2 false alarm probability. It comes from indeed using all of the detections of Kuiper belt objects, not asking, okay, here we have 3 detections. Can we use, you know, and a pointing history of the telescope, can we use that to prove anything? Okay, I think when you have low number statistics, it's much more important. It's much more, when you have, sorry, a small number of detection, the comparison sample plays a bigger role.
Thank you for that. I mean, you mentioned that one for every 500, right? So 1 for every 500 chance. Is that it?
Yeah. Okay. So it's kind of like this. Imagine you go to some place. Oh, like, okay. Imagine you go to Chernobyl. Like, I'm from Russia. Right? So you go to Chernobyl. You find a wolf, and it's got, you know, 2 heads. You find one wolf. It's got 2 heads. With that detection alone, you can't know anything, right? You don't know if that's abnormal or normal. Okay. And then, you know, suppose you stick around in Chernobyl, you find 3 more wolves and they have 2 heads. Okay, and you say, okay, my detection is 4 wolves, they all have 2 heads, but 4 is a very small number. Okay, like that's small number statistics, not really enough to draw anything in particular. Then you go and, you know, to some place like, I don't know, Alaska, and you find 4 more wolves, and the wolves each have 1 head. Still, you know, you might be like, okay, well, I have 4 and 4. Not too big of a deal. But if you know that everywhere in the world there are wolves with 1 head, the moment you find one with 2 heads in Chernobyl, you already know that something bad happened in Chernobyl, right? So that's what I mean by the comparison sample being really important for low number statistics.
Yeah, thank you for that clear example. So I'm encouraging the people here in the chat to, if you do really want to, yeah, here I'm seeing someone raise his hand. That's what I'm saying. Thank you for the leadership. John Dello, you can unmute yourself and to have a first-hand voice-to-voice contact, or yeah, virtual question. John Dello?
Yeah. Hi, Professor K. I am John Dello. I'm from Mindanao. I have many questions, but I think if I have time, I will ask some. But this is my first question. So in the hill sphere, that's the region where the satellites were formed, right? Am I right? Yes.
Uh-huh.
So my question is, can a satellite be formed just at the boundary of the hill sphere?
Oh, just at the boundary of the hill sphere? No, the boundary of the hill sphere is already unstable. So the disk extends to about 0.3. Then beyond 0.3 of the hill sphere, you basically start to see resonances with the sun that make your orbit unstable.
So thanks, Nick. And
okay. You have follow-up question, Jandelo? Yeah.
Not follow-up, but second question. Yeah, I asked. Yeah, since this is a theory, so there must be underlying assumptions. And as I read from your paper, I read the paper. You said that we admit that our assumption of an optically thin nebula. I don't know what's the meaning of that. Can you somehow enlighten us?
Yeah. So basically, what we did is we assumed that the nebula. What we did is we assumed that the nebula is vertically isothermal. Okay, so that is okay to do if you think that the optical depth of the disk going from the midplane to the top of the disk is less than 1. So like basically photons can escape from the midplane all the way to space without getting absorbed and re-emitted too many times. If that's not true, okay, if that's not true, the only thing that changes is the vertical temperature structure of the disk. And then that basically means that where you can start making satellites moves out to a somewhat larger orbital radius. Okay? And it goes as the fourth root of the optical depth.
Yeah. Thank you, Jandelo. We'll move to the question of Sir Austin Liang.
Yeah. Hello.
Hi.
Hi. Could the Grand TAC model have an explanation as to why the Galilean moons formed? Because if I recall correctly, the Grand TAC is where Jupiter moved into the inner solar system. Surely it would have acquired some material from there.
Yeah, it's a great question. So in the Grand TAC model, it's not directly connected to the story because it doesn't really matter where Jupiter is in the nebula as long as it's sort of at the few AU radius. The reason it doesn't matter is, as you saw in those observations, giant planets have a tendency to clear out their orbits. Okay, once they clear out their orbits, right? Even if they move to a smaller orbital radius, they move with the gap, so to speak. So it's not like they fly in and grab Earth-like material. So for the direct purposes of this model, it doesn't matter if the Grand TAC happened or didn't happen. There is, however, one link which is really important for both models. Okay, so both models assume that Jupiter and Saturn formed to their terminal mass, or roughly their terminal mass, stopped accreting, but then lived in the solar nebula for about 1 million years. That seems plausible and reasonable indeed, but I should say that is an assumption, in the sense that we don't have a concrete theory for what sets the terminal masses of giant planets. Okay? This is one embarrassing thing about the core accretion model of giant planet formation, is it doesn't predict what the final masses should be. It doesn't tell you how the accretion process stops. Okay, so that's why we felt it was important to actually emphasize this in the paper, to just be maximally clear that we indeed assume that a planet forms and it's there and it can live in this gap without accreting the remainder of the solar system's gas. But we don't have a solid theory for how that isolation happens.
Thank you. Prof K, we also have here in our audience high school students. They might just be, shy to ask questions, but perhaps they would like to know, how is your high school life like? How you became now the Prof K that we know of, very successful in your field. How do you spend your high school life?
I had a great high school experience. Well, I had a great, but then also at times not so. Okay, nobody has just a purely great high school experience in the world. Okay, like no one goes through high school and doesn't experience and is like, oh yeah, that was fantastic, and I never had a bad day. Okay, let's just be. And I was the same way. So I moved a couple times. I moved around a lot as a kid because my parents moved around. So there were obviously challenges with sort of like switching places. I also moved to the U.S. In the middle of 8th grade, so I just like spent the first 6 months trying to I didn't speak any English, so spent the first 6 months acquiring English, and then started high school. That said, towards the second part of high school, I had a great time. I first of all I played in a band, and we played shows every week or so. This is before San Francisco became lame. Okay, like San Francisco 20 years ago was super cool. San Francisco now is kind of lame. All right, but 20 years ago it was a great place to have a band. And I spent all my time on music. So I spent maybe 80%, 90% of my time on music, and 10% actually on physics. I enjoyed even back then the physics, and I remember I got captivated by early like early just musings of chaos theory. I remember I think I was in junior year. So it was 11th grade, and I remember I came up to my physics teacher. I was like, okay, so how come everything has a solution, right? Like I was like, how come we solve these problems, right? And it just always works out, can it, why is nature designed to mathematically solve itself? And the teacher said, well, that's because we're learning from a book that only has problems with solutions. It's like, I was like, okay, so are there things that are unpredictable, genuinely, that cannot be modeled? And she said, well, okay, they can be modeled, but the solution doesn't mean anything after a while. And the weather is a great example. I remember thinking, my God, what do you mean? So I remember that kind of captivated me, and I started doing a little bit more of my own research, and that turned, this sounds kind of silly in retrospect, but I was like, you know what I should do? I'm going to do a science fair project. Science fair projects, so I did one, and it was actually about particle accelerators, and got really interested in it for a while. So I won the science fair, and I thought that was a great experience. So next year I did it again, and when I was a senior in high school, 12th grade, I won the I went through the ranks where I won the city one, then I won the county one, then eventually I won the the California state one, and I thought this is pretty cool. So when I was applying to college, I applied to half of the schools I applied as a music major, and the other half I applied as an engineering or physics. Yeah, it was an engineering physics major, and I decided that I remember I only got into a couple schools. One was Santa Barbara and one was Santa Cruz. And for Santa Barbara, I got in for music, and for Santa Cruz, I got in for physics. And I thought, okay, if I go to Santa Cruz, I can still keep playing in my band because it's close to where I live, and so I have the best of both worlds. And that was my trajectory. But yeah, I know this is a long-winded answer. Long story short, I was not anything special in high school. I was not a prodigy or anything like that. I just, did my thing, hung out with my girlfriend. I later married my girlfriend. She's not my wife. In fact, she's right there. So, yeah.
Thank you very much for showing us the humanness of being a scientist. And also for showing our high school students, kids here that there's still a lot of things to work on, right? And they're inspired, I think.
Well, I appreciate you saying that.
Yeah. We can accommodate to our viewers. We still have three slot for 3 more questions, so please feel free to key in your questions. But perhaps our we have here from Mikhail.
So, good morning. I'm Michael Mangada from the National Institute of Physics. Am I audible to you?
Yes.
Can you hear me?
Yeah.
Here's my question. Since you have mentioned circumstellar, circumplanetary, and accretion disks, what are their differences and how different or similar are the modeling approaches among these three?
Yeah. Okay, great. So great question. So, okay, circumstellar disk. So traditionally, if you look at the literature, what astrophysicists really like to do is to have the same model for everything. Okay. And to an extent that's okay. Circumstellar disks, however, are accretion disks. And we see this, right? We see the gas sinking onto the star, and we see the emission that comes from the release of gravitational energy as the gas kind of gradually accretes onto the star. The circumplanetary disks are decretion disks because they're vertically fed and the gas is flowing away from the planet. That is not, it seems like it's not a huge difference, but in the end, it's that control, like that simple difference controls how you make the primitive asteroids or the primitive building blocks. So they are quite different. And I should say that decretion disks, these disks where material is flowing away from the planet, are quite unusual. They only happen around planets, and the only other creature that has them are stars that they're called BE stars. BE stars, towards the end of their lives, they spin up, okay, to the point where material, like they spin up so fast that the material just starts going into orbit, and it drifts away from them. So the modeling approaches of BE star disks and the circumplanetary disks are very, very similar, even though they occur on vastly different scales. Just like the modeling approach of a protoplanetary disk is very, very similar to like an active galactic nucleus, right? Disks around black holes. Very much the same equations, even though the two occur on very, very different scales.
Thank you for that. Another here we have question. Because normally Filipino teachers are multitasking and doing some laundry while attending the session. So our teacher here would like to ask on if just in case they would like to invite you to seek for advice for an experiment about physics and astronomy, how they can contact you or reach you?
So by email. If you go on my website, konstantinbatygin.com, my email. Alternatively, I'm on Twitter. I'm also, I guess I'm on Facebook, so you can, all of the above. I'm even on Instagram, but it's mostly for band stuff. I only post pictures of the band on Instagram. So, those three: social media and email.
Yeah. Thank you for that. I think our teacher here already have answered while doing his laundry. Yeah, yeah, multitasking.
Laundry as well, so
all the spinning thing also happens in concurrence. Yeah. Okay. Anyway, actually, we are flooding with a lot of questions here, and we want to give an equal platform for everyone. I think perhaps we just want to ask few words for our viewers now. Prof K, that you wish to impart as you have an audience here in the Philippines? Yeah.
Yeah, I think this is not going to be particularly specific, but I think I have in my life had the opportunity, for better or for worse, to travel quite a bit. When I was a kid, immediately after the Soviet Union collapsed, and we sort of for work, basically my parents, were in a relatively bad situation, financially, but were able to find work. So we moved to Japan, And I went to elementary school and middle school in Japan, which was came with its own challenges. And then we moved to the U.S. And so I guess my my takeaway message is from having lived in a couple different places, is that I think one thing that ties us really beautifully together actually is the science. I think there's I have collaborations in my work that span and are very kind of cross-continental, cross-cultural, and I think that science provides a really nice medium for all of us to to connect and share in the beauty of this of this mathematical description of the world that I think we can all take part in, appreciate, and I think it's one of the most fantastic aspects of the human experience.
It seems like our common language is mathematics and science, right?
I certainly think so. Yeah, I certainly think so. And there's this famous quote. I forgot who said it, but it was some person. Doesn't matter. It was some philosopher who said that the astonishing, and I paraphrase, but the astonishing success of mathematics in describing the natural world is neither something that we understand fully, nor do we deserve it.
Yeah, something we don't deserve yet, but perhaps these words, you will see in the chat our words from our viewers. They're on their key takeaways for this morning session. And David, have we selected perhaps someone from the audience who would give us their key takeaways?
Well, I think I find it interesting, this recent comment from Miss Gabriela Francisco. She said a very nice thing.
Miss Gabriela, if we can invite you to be heard. So personally, you can share your key takeaway to our guest speaker. Miss Gabby? Ma'am Gabby? Or are you there, Ma'am Gabby? Well, anyway, Ma'am Gabby?
Sorry, I had trouble unmuting. I just wanted to say thank you so much. I'm a music major turned 6th grade science teacher, so I'm really looking for opportunities to learn, and I learned so much. I can't say I understood everything, but I will read up. Thank you so much. It's just wonderful to see. Mainly, I was inspired by your passion, Professor K, and I just hope to be able to inspire some of my own students with even just a bit of what I learned from today. Thank you so much.
Gabriela, thank you so much. Thank you so much for your kind words.
Yeah, thank you very much, Ma'am Gabby. David, your floor now.
Okay, thank you, Sir Keith. Okay, so once again, let's give a round of applause to our speaker and to our moderator, Mr. Keith. So it's a very dynamic Q&A, and indeed, we are all sharing that feeling that, yeah, there's still much more to learn. And I'd like to share this. My professor in mathematical methods, Sir Perico Esguerra, shared this quote from Victor Weisskopf. It's better to uncover a little than to cover everything. So yeah, don't just be like Steno. Keep turning rocks over and see what we find. So, okay, thank you so much. Now let's welcome Professor Christine Joy Aban, a faculty member of the Physics Department of MSU Iligan Institute of Technology, to read the audience's response. Prof. Aban, are you there? Is she here? Prof. Aban?
Okay, thank you very much. I was trying to unmute myself a while ago. Anyway, thank you, Prof. K, for your talk, and even me, I have some takeaways. Science ties us beautifully together. So, as mentioned earlier in the program, we want to hear some takeaways and statements you have learned from our speaker, and I will take some time to read some of them. So, what are the lines that orbit into your mind from Professor K's talks? So, if you have some of them, you can write them in the chat box. While we have read some of the takeaways. So, from Austin Bean, he said that he learned a lot how giant planet satellites form and some of the physics behind it. And then from Joseph Gutierrez, planetary formation is very dynamic. And then from Dean De Los Santos, science is not the final answer to any questions. We also have a lot of takeaway message here. Most of them said thank you, Professor Keith, for your wonderful topic and your discussions today, and for sharing your ideas, your generous and very informative ideas. Also, we have here a very most of those participants today gave their thank you. Then we have here from um, Red. Sorry, I cannot read fully your name. He said that he learned a lot from this webinar, especially in how giant planet satellites are formed. And then thank you for sharing your expertise in physics. And we will share the learnings today to your students during their Google Classroom discussions. And then God bless to you and to the physics community. And then we also have here, yes, and then they will thank you for the great information, and that I learned a lot and how it will gonna form, and looking forward for this successful information. So again, thank you very much for your for sharing your topic. And indeed, scientists are human.
Thanks so much. It's so yeah, it's you guys are too kind. You guys are all collectively too kind.
I will now turn you over to our MD.
Thanks, Prof. CJ, and syempre, thank you to all those who sent their key takeaways. No, it's really quite heartwarming to read them and to share them to our speaker, and also to actually know that we are interacting. This pandemic really requires us to reignite our passions in physics, and well, actually not only in physics but in our passions in general, and talks like this really help us a lot. And so once again, thank you, Prof. K, for sharing your insights, your passion with us. I really believe that passion is transmittable. If you're passionate enough, if you are glowing enough, that light will be shared all over the world. So yeah, parang one child at a time is the goal. So thank you, thank you, Prof. K, for that. So before we have our closing remarks, would you like to share any more final words for our participants, Prof. K?
Well, no, I just want to say, thanks to everybody. I know that it's I know I ramble on quite a bit, particularly when it comes to satellites, but just it's been really really a pleasure to spend my evening, your morning, with you guys today, and all of the positive energy that you guys are transmitting over Zoom is just so fantastic. And I really really appreciate all of you guys' positive comments, and we'll get through this pandemic soon enough, and then we'll hopefully we'll all be in real life again.
Thank you for those words, Prof. K. And yes, it's very hopeful thing to say. We'll be in the real life again. Okay, so now we now welcome Dr. Cecilia Bukayong, the Director of Governance of the Physics Meetup from the CMU Physics Department, for the closing remarks.
Hello. Hello, everyone. Good morning here in the Philippines. Greetings. Indeed, it's overwhelming to be working under ICTP Physics Without Frontiers, for the chance of having an astronomer as our speaker. We were given the privilege to virtually interact and ask questions live and for free. Thank you, Prof. K, for sharing to us very informative topics about satellites and beyond. Thank you, thank you. And congratulations to our team, since we are already in our 17th physics meetup and counting. And take note, it's not only our session that is gradually increasing, but we also are growing in number in terms of our volunteers, facilitators from all over the country, represented from different scientific and professional organizations. Hooray! Of course, with this increasing partnership and growing family, we are also expectant for more coming our way, for more high caliber scientists. We are also expectant scientists for our speakers, and of course, consequently, an increasing number of physics enthusiasts who will be joining with us. Are you excited? Because I am. Okay, let me end by thanking our volunteers for today, hosting this very successful event. Of course, to our speaker, Prof. K, thank you very much. And to our MC, Mr. David Marik Makatangay from UP Diliman. And to Professor Lotis Racines from CMU for introducing to us our speaker, and to our Q&A moderator, Mr. Christopher Castillo, Foreign Service Officers of DFA, and our response facilitator, Professor Christine Joy Aban from MSU IIT. And of course, to all who join us today, thank you so much. We are hopeful that for your support. Continue supporting us for our coming sessions. Thank you, and God bless everyone.
Thank you, Dr. Bukayong, for those closing remarks. Now, we're down to the fourth and final part of our session for today. But before we go to that, which is the networking part, we would like everyone to open their cameras for a Zoom groupie. Okay. So if anyone could open their cameras, if possible, we would like to see your faces, faces that are either happy or confused, like me. I'm confused, although I'm smiling. Okay. So, okay. I will be taking a screenshot. There are actually multiple frames, so if you would bear with me while I take a screenshot of each part. Okay, there are actually 11. So please bear with me as I take a photograph of each one. Okay, so kaya natin to. Okay, ready for the first frame? 1, 2, 3, smile. Okay, I've got that. Now let's go to the other parts. Wait, I'll have to paste that first. Please bear with me. Okay, next frame. Okay, 1, 2, 3, smile. Okay, now we're going to the other frame. There are 11. I'm only down to 2. Okay, so here, 1. Oh, we're done. We've got all the frames already.
It's like an injection, you know, like when they go 1, 2, oh, you're done, you know. Good.
Are we okay now? At the ads or okay, they took it already. Okay, thanks. Okay, thank you, and thank you to all our participants. Now, before you all go, let's if we would like to join us in our networking session, I would like to turn this over to Prof. Bien Botanas, co-coordinator of the Physics Meetup, to facilitate our networking session. So I hope we'll have fun in that networking session part, which is very exciting because it's more informal and you get to be more friendly in that session. So, Prof. Bien. Prof. Bien there?
I'm sorry. I'm waiting for the dogs to.
Ah. Yeah. Okay. So while waiting for Prof. Bien's neighbors' dogs to stop barking, how are how are you guys? I mean, I love going to physics meetup. I always say this to everyone whenever I'm going to be sharing my insights. I would always say I'm happy to be part of the sessions because I don't know about you, but I'm starting to somehow question why I chose the physics track sometimes. But whenever I'm joining these sessions, I get to realize, oh, that's why I joined because I am curious. And it's just satisfying enough to be curious and to have your curiosities answered. You may not be able to be correct all the time, but at least you get to be satisfied with the fact that you're able to somehow get to answer the questions. Although you may not be able to get the right answer, or you may not be able to get an answer at all. But it's fun. And I think that's one of the things that we learned here in Prof. K's talk, and that is science isn't a final thing. We keep on learning new stuff and we keep on asking new questions, and that's what's very interesting. So I hope you share the same thing, and I hope to see a lot of us to keep on moving into these sessions. It really helps us to keep sane. I don't know about you, but it helps me keep sane. Yeah.
Thank you, David.
So
Yeah.
yeah.
Just give a virtual round of applause to David. Amazing. Thank you so much for your awesome work. We also thank Kuya Kit. Thank you once again. And of course, Professor K, thank you so much. Mom CJ and Mom Lotus, thank you so much. We're
Thank
happy.
you.
Are you having fun right now?
Big time.
Can you just show your thumbs up if you're, yeah, I love it. I love it that you're clapping your virtual hands and you're raising your virtual thumbs. So thank you so much.
Yeah, I'm sorry. I'm sorry earlier. Since our dogs are barking, so I'm not comfortable with the noise. So that's please bear with me. But I'd like to thank Professor K for that wonderful talk. It's been a humble experience to have a scientist who talk about formation of satellites, and we've learned really a lot from you. And hopefully our students will somehow in the future will pursue this field. So I think physics is pulling us through this platform. So hopefully students will really pursue science and of course specifically pursue physics. Well, I'd like to invite everyone for this networking. I don't know how to facilitate this one, but then I'd like to classify this since Philippines is actually composed of three main islands. We have Luzon, Visayas, and Mindanao. So I think let me start first from Mindanao. So I'd like to hear one teacher, and then after that one undergrad student, and then one high school student, and if possible, if there is an administrator in the Department of Education, so you can also give us some of your thoughts. So let's start from Mindanao. Maybe please raise your hand and then say something. State your name, where you come from, and then state whether you're an undergrad, you're a teacher, or an administrator, and then say something about what you'd like to say in the group. So thank you. So let's hear from. Is there anyone who would like to start from Mindanao?
Sir David Paul. Sorry. Oh,
Yes.
Hello,
Yes.
good morning, everyone. So, I'll take this chance to start the networking session. So, I am David Paul M. Hinayon. So, katukayo ko si David, ano. Um, um, and I am an undergrad student, currently a third year from MSU IIT Mindanao State Iligan Institute of Technology. And Mindanao for Prof. K. So, Mindanao is actually the on the southern part of the Philippines, so one of the main islands of the Philippines. So yeah, this session has been fun, and as what David said, our MC David has said, this meetup has always been a source of inspiration for us who's beginning to question our place in this course. So it's been a pleasure to hear your talk, and it's a pleasure to be here. That's all I'd like to say. Thank you.
Thank you, David. Thank you for your kind words.
Hi, sir. Hi, sir.
I don't know about you, but I like this music. I think it's coming from Kent Kuyos. Yeah. Would you like to share something, Kent? I like the music though. I really liked it.
Sorry, sir. I'm in the church.
He's in the church. Okay. I hope you're doing well. Thank you for taking the time. Oh, sure. It's all
Sorry,
right.
sir.
Thank you for taking the time to be here. Okay.
Thank you, sir. Thank you for for the information, sir.
We have Sir Joseph Gutierrez from the Department of Education. Would you like to say something?
Oh yeah, thank you. My name is Joseph. I work with the Department of Education. I actually am working at the Bureau of Curriculum Development. So we do research, we develop the curriculum standards, the learning standards for our basic education learners. I was a classroom teacher for more than 2 decades before finding my way to the central office. And I used to be a part of a local astronomy group for more than 10 years. We do astronomy outreach to high school kids. On a personal note, I am also doing some personal outreach in my local village. My target audience are usually elementary and high school kids. I teach them basic astronomy. And then listening to the talk of Prof. K is really something that reminds me of how beautiful astronomy is and how fascinating it is. Thank you very much for having Prof. K today. It was such a wonderful thing listening to him. Thank you.
Joseph, thank you so much for your kind words, and it's so wonderful that you're doing this this awesome outreach outreach work. I mean, it really matters, and it makes a difference. And thank you for your hard work on this.
So we are really happy for this gathering, because I think most of the participants are mainly from science, and then this is the only I think this is the only avenue where we actually hear from an expert, say something about the field, and then invite them to pursue it. So it's really nice to have this kind of environment. So I'd like to ask if there is a high school student from Mindanao who would like to say something. If since there's none, so let's move to Luzon. So who would like to? Okay, there's John Lester Cañete. Okay, John, please say something.
Okay. Can you hear me, sir?
Yes.
Yes, sir.
Okay. So, I am John J. Pinete from Maragusa National High School. I'm currently in grade 12 with a strand STEM. So I just want to say thank you to Professor K and to the institution behind this physics meetup. And to be honest, I don't love physics that much. So, and I find this meetup very interesting, and I think this is a stepping stone for me to love physics more. So, thank you very much.
Awesome. Just awesome.
Thank you, Professor K.
Thank you.
Thank you so much for that. It's really nice. Let's now proceed to Luzon. So is there anyone from Luzon who would like to share their thoughts? So we'd like to hear from a high school student first, I think, if there is.
Yeah, hello.
Santo is raising her hand. Serbian.
Santi Arnado, so you're recognized.
So good morning, Professor K. I'd like to thank you for that very informative talk. Something I'd like to share is that before I'm a senior high school student, so I'm in the 11th grade. Before I graduated junior high school, I wanted to be an astrophysicist. But then recently doing research, been doing I've been more into material science, but I'd like to thank you because of this talk. I think I kind of gave up on that dream because, as many of us know, pursuing a career in astrophysics here in the Philippines is kind of overwhelming since the field is not that, well, I wouldn't say it's not that well known, but it's not something normal high school students would think of. I actually wanted to be an astrophysicist because of Sheldon Cooper, who I think is portrayed as also from Caltech. So having these kind of sessions made me recognize the reach that I have. I mean, before Caltech seemed like a university far away, but now hearing you talk and hearing you share those information to us made me realize how achievable my dreams are, and I'd like to thank you for that.
Oh
Thank you, sir.
wow! All right, thank you so much. Yeah, that's really heartwarming to hear. You know, I think astrophysics is something that is kind of obscure, really. You know, in most parts of the world, right? And all of that said, I think, you know, if that's really where your passion is, I would just give it a shot. You know, if that's what you want to do, if that's really what resonates with you, then I think, you know, go for it. And one other thing, I know that I'm not trying to take over the conversation or anything, but one thing that I found over the pandemic is actually gave myself a bit of a challenge to actually start doing research in things other than astrophysics. So I started doing a bit of research in material science. So you and I are going the opposite directions. And what I found is that the mathematical methods are exactly the same. So I have a paper in review on, on stuff about irradiation of nuclear waste with proton beams and stuff. But a lot of the mathematics really carries out. So I think what, I guess I would encourage, if your passion lies in one particular area of physics, it's not like, if you go and you develop your skill set here, it's not applicable here, right? It's all just, there are not that many physics laws out there, and they're all, moreover, there are not that many equations, right? Once you figure out how to solve a few of them, you kind of figured them all out. So I think it's, anyway, I just want to say thanks, and it's very encouraging for me to hear.
Thank you so much, Santi. I'm happy that you joined us today. Santi is somewhat a very active student from Manila. So I think this is her, I don't know, second time, third time being part of this meetup. So thank you so much, Santi. You're such a promising high school student. So how about from a teacher or administrator from Luzon? Anyone who would like to say something? I'd like to ask help from my colleagues if I won't notice somebody raising hand. So just tell me if someone is raising their hand. How about undergrad student from Manila?
Oh?
From Luzon, undergrad student from
Ryan Kutamora, Sir Ryan?
Okay, so good morning to everyone. First of all, we would like to congratulate and give appreciation to Professor Konstantin. Prof, thank you so much for informing us about your field, your expertise in astronomy, as well as with your topic that you have discussed today. Well, actually, um, I'm a biology major, and it was a surprise to me that actually, I have no interest at all about physics before when I was a high school student, but that's why I pursue biology, right? But when I became a college instructor at Cavite State University, during 2010 to 2014, before I transferred to Department of Education, I became a physics instructor there. So, ayun, I really love science and teaching physics and specifically astronomy is a way for our youth to become aware of our universe, our surroundings. That's why, because of this networking, right? I would like to invite Physics Meetup. Thank you, Physics Meetup, for inviting us here today. Together with my classmates in our masteral group. So, marami po kasi dito ang mga biology major from Cavite. And we would like to invite you, Physics Meetup, to join, to invite us, our learners from the senior high school, because I wanted them to learn more about physics, Kasi compared to other field of sciences, medyo napag-iiwanan yung ating linya. So, puro na lang kasi biology, puro na lang kasi chem. So why not naman na medyo we give more investment to physics, right? So I am willing to be your volunteer to build linkages between our youth here in especially in our municipality of Carmona, Cavite, and with your organization. That's all. Thank you. Since I am the secretariat of the local school board, I am willing to be your partners for your organization.
Oh, thank you so much, Sir Ryan. So it's really important that we had this gathering, since we know that physics is only a small community in the Philippines, but then seeing this population right now is somewhat kind of boasting, and then we want to know that we want to inform students who are here that we have this community that that works in this field. So we have this presence. So hopefully they will really find something and pursue a career in science. So how about an undergrad representative from Luzon? Austin? Is Sir Austin Diang an undergrad or
Hello. Yeah, I'm
Yes, sir.
I'm a senior. I'm junior. I'm a junior high school. Wait, I'm a senior high school student. Grade 11.
Serious?
Okay. So, would you like to share something? Since I think you're from the way you asked questions earlier, so somewhat, I thought that you were in the undergrad because I think from the kind of question that you are asking, so somewhat you have something.
No. I just, I've been reading a lot about astronomy.
Okay, so thank you for that. So let's move to Visayas. So anyone from Visayas, an undergrad teacher or yes, Ma'am Sabelia is raising. So, Ma'am, you are recognized. Ma'am Gina, go ahead po. Hello, Ma'am Gina. I think so.
Yes, sir. Hello.
Okay, ma'am. Go ahead, ma'am.
Okay, good morning to all my co-participants from the Philippines and good evening, Prof. K. I'm Gina Sabelia from Sinsi National High School, Cebu City Division. Thank you so much for this very informative morning. I am a general science teacher, but I have a lot of interest when it comes to astronomy. And I'm so happy for this morning that I was able to have this interaction with astronomer from in the person of Prof. K. So thank you so much, and physics meetup, thank you also for this opportunity. Thank you, everyone. God bless.
Thank you, Ma'am Gina. We would like to entertain one more student from Visayas before we will wrap up this the session. I'd like to ask Mama Del to do the wrap up. So I think nobody is raising their hand from Visayas. So, Mama Del, go ahead.
Okay, thank you so much, Sir Bien. Sir Bien is the co-coordinator of the Physics Meetup, and we're so happy to partner with different organizations in the Philippines, not only from Mindanao. I think, again, couldn't thank you enough, David, Sir Kit, also Ma'am CJ and Ma'am Lotis, and of course the team behind all the running and organizing of this session. So thank you so much to the participants experience team and also the student assistance team who provided the load assistance to 150 students. So thank you so much for all your hard work and also the documentation and session programming. And of course, we want to thank again Professor K. Thank you so much for accepting our invitation. Professor K, thank you. We want to give you a certificate of appreciation, but we will send it in a few days because we will collate all the messages from the participants and send them to you. So thank you so much for.
So nice. Thank you so much.
So we are excited also for that. So you need to spend like a few minutes to go through all the messages, because sometimes it would take like 58 pages, 50 to 60 pages. So that's
956.
so that's how long they write messages to our Thank you once again, everyone.
Miss Ads, I think Christine Ipanag would like to share something. She just can't use the raise hand function. Christine May Ipanag, are you there?
Thank you to physics meetup. Just to add what Nancy said a while ago, born in the Philippines, really inexperienced to pursue a degree in astronomy. Already explained that astronomy is so hard for new students to achieve, but this physics meetup has turned my way of thinking that there really is other way around. If you are just passionate with your dream, your desires in life, and you will take all the odds, all the struggles that comes your way just to have that dream of yours come into a reality. So thank you, Prof. K, and the team behind Physics Meetup, and as well as the moderator, the host, and to everyone that who is joining. I really appreciate all your efforts, all the knowledge you have shared, and I hope to see you all soon in the next meeting. Thank you, Mom. Thank you, sir.
Thank you, Christine. Thank you so much once again. Before we close our meeting hall, because we want to also respect the time that we had committed to everyone and also to Professor K, we want to invite you, if you want to volunteer in the physics meetup. This is a collaborative community, so anyone can volunteer as host, moderator, or helping us in preparing for the session. So you are very welcome. Just connect with us at physicsmeetup@gmail.com. And we would also like to invite you for our next session, which would be on April 9. And this is also he is also an exciting speaker. He's a Filipino American, and we just want to give a hint so that you would go through the poster that we will publish probably this week. So our hint is he was one of the key persons for the NASA Perseverance rover on Mars. So you're excited for that one. So thank you so much. And we want to thank our speaker because they are doing this. Professor we'll have to end this and probably say our goodbyes before I close the meeting hall. You can unmute your microphones and say goodbye.
Bye, sir.
Thank you.
Bye, sir. Thank you, sir. Thank you
Goodbye,
very
sir.
much.
Thank you.
Thank you, Professor K.
Thank
Bye.
you po.
Thank you,
Goodbye,
sir.
Thank you, everyone.
sir.
Professor
Bye-bye. Thank
K.
you.
Bye. Thank you very much. Thank you. Thank you.